Okay, so let's wrap up everything on SVM. So before we wrap up the SVM, let's and finish up the last things. And previous all the SVM, we only work on the binary situations. Right, so like basically zero, +1 or -1. In fact, that's the most commonly used and a situation in SVM. But in many situations you want to use SVM on multi-class situations. So how can we work on a multi-class SVM? So this is very important. Think about the data of MNIST and a data set. So you have Y label is from 0, 1 until the 9th. So that means we have 10 different labels. So, and then there are two possible ways to work with. There are two strategies to work with. First one is 1 and 1 against all. Scheme. So basically, and what we do is we can construct say K, and if it is multi-class with a K different classes, K binary, SVM, with a parameter. For example, the WJ and the W0J. So what is 1 and 1 against all? And the situation you can think about in MNIST data set, you are creating the situation for 0 and versus none and not 0, 1 versus not 1, and so on. You have 9 versus not 9. So basically you have 10 different SVMs to work with. They are all binary. So you train these 10 and different and binary SVMs with and one against all. So basically this is and each classifier are the current class of J and against all others. So once you train this, so this is the first and step 1. And step 2 is, this is training. If you are giving a new data, and what you do is you are going to make predictions for all these 10 SVMs one by one. So basically, and you are going to, say we do the kernel version of phi x, which if you want to use in linear, just assume this phi x is is equal to x. And WJ plus W0 J. So this is my so basically, and you can think about the distance from from this current point to my decision boundaries for all these 10 different binary SVMs. So I want to find out the further the point from these decision boundaries in the positive directions, it's more likely to belong to that class. So this is, and you calculate this and one by one, you're going to do argmax of J from 1 to the K. So this will be my predicted class. That class is it's like that. So this is basically we train this 10 like different SVM for 1 against all. Then you have a new data you plug in and you want to find out and the point from decision boundaries in the positive directions sorry, the distance between the point to the all 10 and the decision boundaries in the positive directions. And the further that we got, it's more likely to be that classes. Okay, so this is basically the whole idea. Because if it is like further away, and the probability to be that classes will be significantly higher. So this is the philosophy underneath of that. So this is and the multi-class SVM, and this is the first, and the strategy is one against all. The second one is one against one. So, and what we do is we are going to, step one is we are going to construct a binary SVM for every pair of classes. So in total, you will have a k times k minus 1 divided by 2 pair. For like this k-class classification problems. And so in the MNIST data set, that will be, say, 0 versus 1, 0 versus 2, and so on. The last one will be 8 versus 9. In total, you need to handle with 10 times of 9 divided by 2, which is 45 different SVMs. Okay. So this is the training. Step 2, if you are giving a new data set, a new X right here, you're going to test on all k times k minus 1 divided by 2 SVMs. So basically, a win is for the class. Win for one class is a vote for that classes. So the most wins, and the class with the most wins is the predicted class. So basically, you can think about this as like at boxing, but in this case, you will have 45 boxings. They're going to try this 45 boxing cases one by one, and for each of that, you will have the winner, right? For example, the first one could be the winner 0, the second one could be as 2, and so on. So then you count how many wins they have for the 0, 1, 2, 3 until 9. Then the class with the most wins, and with the most wins will be that and the predicted classes. Okay, but in this case, you have to do this 45 times for the MNIST data set. Okay, so this is the situation if you have to work with multi-class and the situations. All right. Okay, so and then let's make summary for the SVM and the logistic regressions. It's a summary of SVM and the logistic regression. I think we spent really a long time on this part. So let's wrap things up. I think we already spent almost 3 weeks and the lectures on this classification problems. Okay. So the key is we want to construct a decision boundaries. a decision functions, and let's call it a decision but this decision function is also called classifier as well. Depends on, we can talk about this. So here I'm going to call this decision functions being f theta of x. Okay, so this is an r small d into the r. So and we have a parameter, so theta is some parameter here. Okay, and of course we can, and this is, and we can have a linear model. I don't want to put a here. It's just so with the linear model, that means my f theta of x, it's nothing but my x times w plus w0. So my theta is nothing but w and the w0. Or you can have some feature map, and this feature map, it will be something like f theta of x. It's like nonlinear models. So this is basically nonlinear models. So you have some feature map of phi of x, w plus w0. Okay, so of course in this cases, so this w is in r small d. Let's say my feature is in r big D now. Then then with the nonlinear models, my theta is just being w and w0. Okay. All right. So yeah, and where phi x is feature map. Okay, so this is basically our goal here, and we want to construct a decision function of like of phi theta of x. The second thing that we can and we need to do is, once we find out this, we need to create something called decision boundaries. So what is decision boundary is my decision functions equal to 0. So that means it basically separates these binary classification, to two parts. One will be +1, one will be -1. So in one one direction would, and that will be +1, and in the another direction that will be -1. It's by usual conventions with this decision boundaries, we usually say if you have a new data and my y is equal to +1 if my f theta of x right here is bigger than 0, it's -1 otherwise. So this, I'm just being said, and just this is my so my sign, and then so actually and determine so which label is, and what is my labels and for this situations. And also we can define something, the magnitude of f theta of x, right? So this is basically, it's equivalent to say it's how far away of my x from these decision boundaries. Okay. if it is far away, I mean, this is also equal to y times of f theta of x. Right, so this is basically what we already have. And then this is just tells you how far away of x from my general boundaries. And as I said, and this is basically say the sine of f theta of x. So, so predict the class. And another part is also very important. If this sine right here, one and a y times of an f theta x, as well indicate whether the x is correctly and classified. So the sine of this just indicate so whether the x is correct. I mean, so whether is x is and correctly and classified. Right. So if it is positive, that means y and f theta x has the same sign. That means it's correctly classified. If y and f theta x are like in a different sign, that means the multiplication will be minus. Then that will tells you like this will not be correctly and classified. So this tells you if the sign of this thing tells you if this x is correctly classified or not. And so basically that means if it is plus sign, it's correct. If it is minus sign, it is wrong. All right, so number 4. And also, I mean, this is just being, and up to now we are just building the models. We're building a model, we want to find out some general boundaries. I mean, if it's on the positive side, that will be classified as like +1, negative side will be classified as like negative. Then this can be compared with the ground truth as well, and to see how good of this classifier are these general boundaries and to separate these data. And now, I mean, and we need to like build a training. So basically choose some a decreasing like loss functions. It's very important. This is decreasing loss function L from R to R. It basically like penalize the discrepancies between model output and corresponding labels. So it want to penalize the discrepancy between y and f theta y, so f theta x. So, and so that's why we want to say if y multiply f theta of x right here, if it is small, I want this loss value to be large. If this quantity is positive or large, I want this my loss function to be small. So that's why I can define this as being a z. And my loss function of LZ is decreasing. So this is the key, right? So that indicates the more positive a z that we have, and my value is smaller. All right, so that's so that's a choice of the loss functions. And of course, we can talk about this and the loss function. It's a little bit later. Number 5. Oh, so then we're going to, I'm actually train it out, right? So basically, and what we actually input is just y and multiply f theta of x. So if we have a training data, so training. So if we have a training data D, it's x of I, y of I from 1 to the n. So a generic way, the generic form of my objective function is I want to minimize the theta of lambda summation of this loss function I from 1 to the n loss functions of y multiply of these quantities. So I mean, everything that matters is just y multiply this in the classifier plus the r theta right here. So this is actually a sum regularizer. So regularization term. All right. So for example, this like very generic framework actually can fits in almost all the problem that we already talked about. So this like generic framework is very important. For example, if we have perceptron, which is the first model that we talk about on the logistic regressions, the classifier that we choose is just a linear classifier, x times w plus w0. Then the loss functions is 0, 1 loss. So that means L, I'm going to call Z, is 1. That is Z less than 0. I have a no regularization. And so we minimize the total number of this misclassified training examples. So, and basically we only have the first component that we have. So we solve by SGD. Of course, we don't have a true gradient. We only have a fake gradient. Okay, so this is something that we did on the perceptron. The second thing that we did is just an logistic regression. So we have a classifier that y is equal to x w plus w0. So what kind of loss function that we use right here? So I'm actually the loss function here. I didn't like mention that very explicitly, but if we compare to the result that we already have, so this is something called the log loss. So what does that say is my log loss, LZ is equal to log of 1 plus of exponential of minus z. So what does that actually mean? So so basically, if my y is for +1 and -1 right here, then my probability of y given x and theta is basically the probability of this. Right, so this is basic says I have log of 1 plus exponential of minus y of x w plus w0. Okay, so this is basically my probability, and if you actually and plug in and on what we already have, this is basically the and the total loss that will be just being the and what we had on the cross entropies, on the cross entropy losses. All right, so I mean this is my loss, and also I have and no regularization. It's equivalent with minimize the negative log likelihood when the probability is defined above. So basically, the key of this logistic regression is it actually has probabilistic meanings. And in minimizing this loss function, it will be equivalent with minimizing some, the corresponding negative log likelihood. And we solve by STD with the true gradient in these cases. So we have the gradient informations. Number 3, we have a hot margin. And a hot margin SVM. So my classifier is still this f theta is equal to, so I think this is I call f theta. My f theta x is still linear model. And my loss function right here. So let me think. So let's talk about soft one first. Soft margins. So we still have the same classifier, but the loss function is the hinge loss. So the hinge loss says the z is equal to maximum of 1 minus z and 0. And we have so like L2 regularization. So that means I'm adding this square of 2 norm of my weight W. And what is this soft margin SVM doing is minimizing the hinge loss with my L2 regularizations. So what we do here, and to solve the soft margin, you can either solve the primal problem directly, with SGD, or what you can do is you can solve the dual problem with SMO. Either will be fine, but just be sure and to see what kind of situation you want to work with. And And particularly if your feature is really large, you probably should work on a do problem. If your number of features is small, you can just directly work on the primal problems. All right, so then I changed these things a little bit from hard to soft, because hard margin in these cases is, you can think about, just we set the lambda to go to infinity. Same as soft margin classifications. Soft margin with lambda equal to infinity, or set of very large numbers. So that will be equivalent to solve the hard margin problems. And usually what we do is we solve the problem with SMO. That will be much easier. That can ensure this is actually to solve when lambda is infinity, rather than some large number. Of course, you can solve the soft margins with the lambda is super large, which is almost equivalent with the hard margins. But if you really want to work and get result and for the hard margin, and you should just work on and solve the do problem with SMO here. All right, so at last we have kernel SVM. So and for kernel SVMs, this f theta of x is actually the phi x of w plus w0. And we know this is, we don't like directly work on this, and this becomes something like summation of I from 1 to the n of alpha I, y of I, then kernel of x of I and x plus w0. Okay, so and everything can be written in this way, basically using all these training values from x1 to xn. The loss function, we are using hinge loss. And then we have L2 regularization. So again, we minimize the hinge loss with the Tikhonov or L2 and regularizations. This is solved by do and solve the do problem with SMO. We cannot using gradient descent directly here. Okay, so but the key is you need to make choices of what kind of kernel that you can and you want to work with. You can either using polynomial kernels or Gaussian kernels. So these are the and two popular ones. Kernel or Gaussian kernel. In the homework, last homework you already did like similar, and a similar practice on these problems. All right, so and you can, in fact, you can further expand this everything into setup for regressions, because this whole idea is very much universals. And the difference between classification and regression here, it just lies in on the prediction part, whether you want to make this prediction to be +1 or -1, or some like continuous like continuous target values. In fact, you can basically work on everything for the regressions if you want. So SVM for regressions. So basically, we actually combine everything together. So we still have the same thing, but instead of we have this loss function to be y times and y times of f theta x of I, and we can make things much more general. That I want to minimize the theta of lambda summation I from 1 to the n L of yi f of x of I and the w. So here we are not like multiply them together. We just want to make sure my so my model and output should be as much close as yi. So I don't have any properties for the plus sign and the minus sign like what we had in the SVM directly. Then we are going to add in this and the regularization here. So this is a very generic models for regressions. So this is the functions of, so this is actually a functions for regressions. And you can have like functions, for example, you can have functions being like phi x times w, which is the linear functions, but with the and with some like nonlinear features right here. Or even some like Gaussian basis. We have talked about the kernelized version as well. But I'm going to revisit and the things we already talked about in the picture of SVM, then we can like propose something more for other losses. Because right here, I mean, this loss is like very generic. We can propose with different and kind of loss if we need it. For example, we can propose the ridge and what we have for the ridge regression. That is my loss right here is just being a square loss. That means it's just the difference is between the output and the ground truth, then we square them out. And we have reg and the L2 regularization. Which is square of 2 norm. In lasso, and you can think about we are still using square loss. It's the same, but instead of we using LY regularizations. So that means we're only interested in 1 norm instead of 2 norms. But for example, you can change all sorts of different loss if you want it. So this is something called epsilon insensitive. Sensitive loss. This could be something like, but this is quite important even in the and for the regressions. So this is basic says maximum of absolute value of x f of I w subtract f of and y of I minus epsilon and a 0. So that means if this value right here is less than epsilon, that means it will just be replaced by 0. If this and and this is and the difference between the truth and the output is bigger than epsilon, it will be replaced by this value and subtract by an epsilon. Of course, you can put L2 regularization if you need it. So this is, and the fourth one is called Huber loss. So that my loss function becomes like that. I'm gonna call it this way. I'm called a function of the differences between yi and f x of I w. So, and you can see right here, I mean, actually, what matters here is not the multiplication of the y times this output. In fact, it's the target and the ground truth, and which is target subtract the output, and which is the residue actually matters. So this is actually the residue here. And the same here, this is also the residue. If you change the sign, same here, this will be the residue. Okay, so, and you can see right here, I mean, in fact, in the regression, what you should put here is actually the residue here, which is yi subtract f of xi and the w. Okay, so this is my residue here. This h function is defined as this. This is equal to r squared if absolute value of r is less equal than c. It is equal to 2c absolute value of r minus c squared otherwise. This is something like very interesting. So this is, I mean, the function of like h right here looks like something like this. So this is basically like we have like straight line and a straight line beyond this domain of minus c to c. But this is being a quadratic functions in between. And the key here, it's also differentiable at minus c and c. So basically, you can always using gradient descent to solve these problems. So this is a mix of quadratic and loss functions. And also you can using L2 regularization if you need it. But the benefit to using this Huber loss is, so the advantage is it will be very robust to outliers. Because this will be some like mixture of the quadratic and the linear. So that means this will be quite insensitive for those and for those loss that is beyond the minus c to c. So we are not like gonna square them out. So this is big and just being and the linear increases, and everything in the middle will be quadratic because quadratic is smooth. It's like differentiable, and we can always find derivative. And also this function is differentiable on the boundary as well. So so this I'm basically being a mixture of quadratic and linear. So everything will be very and we take the both advantage of the quadratic and the linears. It's a robust outlier. It's differentiable everywhere. Right, so this is and basically I mean solve the problem that if we're using L1, I mean it's not differentiable at point of origin. If we're using L2, it will be sensitive to outliers. If we're using Huber laws, it can solve both problems at the same time. Okay, so let me show you some figures here. First thing, you can see these, this is a possible loss that you can choose in, the classification problems. So we know this loss function has to be monotonically decreasing. So these are all possible choices. For example, hinge loss, 0-1 loss, exponential loss, and the logistic loss, which is and it's also called like log loss, which is log of 1 plus of exponential minus e here. If you actually plug in, this becomes logistic regressions. So you can see all these laws, they are monotonically decreasing. And the most important part is these three parts, exponential loss, and the logistic loss, and hinge loss, they are all convex relaxations of the 0-1 loss. Like 0-1 loss, it's not convex, but all the other threes, it's actually convex. So if it is convex, it will be has a lot of and good properties. And they are all like smooth convex relaxations to the 0-1 loss. But the hinge loss is something called and can be solved with subgradient. It's not precisely smooth, but it's the but that's the it's convex relaxation, but that's not a smooth convex relaxations for the hinge of the 0-1 loss. So I would say this way. Okay, so let me rephrase it. And the logistic loss and exponential loss, they are all smooth convex relaxations. But hinge loss is just the convex relaxation. It's not smooth. Okay, for those laws that we talk about, square loss, epsilon insensitive loss, Huber loss is something like that. If we put the residue y minus mfx right here, you can see epsilon insensitive loss, that will be something like this. So this is being like linear growth on both windows, but everything in the middle, that will be epsilon. So that means I will allow some like epsilon differences. So this is called epsilon insensitive. Huber law says that everything in this domain, that will be a quadratic. Everything outside of this domain, that will be a straight line. So it basically combine the advantage of the square loss and also the linear loss and absolute loss that we have. So, and for the square loss, you can see this value, error values is gross and a square way and getting really large if the the residue is really large. So that will be very sensitive to outliers. Okay, so final note on loss functions. All these regressor and the classifiers can also be constructed with something like mix and match strategies. But we didn't do a lot of mix match because different classifier, different loss functions, different and regularizations has different effect. It will suit to a different applications. For example, this L1 SVM right here, we have a hinge loss plus this L1 as L1 regularizations. So that basically we are penalized and we are actually penalized and we are trying to enforce the sparsities of my weight in these situations. The square and the least square SVM right here is we can just and basically square the hinge loss. We can also do that if we want, and we can still put the L2 regularizations. So we can always do mix and match in terms of loss and the regularizations if we need it. Depends on what kind of your needs. We can choose different versions of loss functions and and the regularizations. But you can see right here, I think the last touch or the last node that I want to mention here is in classifications, you can always put this z equal to y and multiply f theta of x right here as some value quantities, and that's something that we want to input as our input during the training. On the other hand, so this is basically, and you can think about as being the an output. The input for my loss functions. But in regressions, what you should actually put here, it's to be more precise, is it's this y minus the fxi. So this is basically the residue right here. So what you should put in is actually the residue of the regressions models, as we are shown right here. Okay, so these are all the residues. These are all the residues. These are all the residues. These are also residues. The residue is my input of my loss functions in my regression problems. Okay, so that's everything I want to talk about. To combine, basically we combine everything on SVM, even with the regressions as well, with the various different and regularizations, loss functions, and a different problem as well. So everything up to now can be all combined into this unified framework if you need it. So this will be a very, very handy if you want to construct your own problems, your own and a classifier, your own regularizations, your own mix and match with loss functions and the regularizations. Okay, so that's everything I want to talk for this lectures.